So today we get to finish up by looking at dark matter, dark energy, and the fate of the universe. Our goals for learning are, first of all, we want to understand what we mean by dark matter and dark energy. So what do we mean? So these basically are two things that we can't really sort of see directly or observe directly, but we see the effects of them. We already have talked about dark matter when we talked about the Milky Way galaxy and the rotation velocities of the stars within the galaxy. And basically what we concluded about dark matter is that it's an undetected form of mass. It's emitting little or no light, but we know that its existence, exists, because we can see its gravitational influence. Now, dark energy is something we'll talk about towards the end of this show. And its name probably is not a great name, but I think it was used because it had a nice sort of symmetry with the idea of dark matter. Again, it's something that we don't really know what exactly it is, so it's an unknown thing, but this time it's energy. And basically what we'll see is it's some sort of energy that has or gives the universe a repulsive force that causes the expansion of the universe to accelerate. So it's working against gravity. So what do we have in our universe? Basically, we'd say that probably only about 4% of the material in the universe is what we would say is ordinary matter. That includes both material that is inside and outside stars. We see evidence that a very large amount of the material in the universe is dark matter, and then finally an overwhelming amount of material in the universe is dark energy. So we want to understand why we think dark matter exists, and then we'll also look at some candidates for what it might be made of. So you might remember a curve similar to this when we were looking at the velocity curve for stars in the Milky Way galaxy. It looks sort of similar. But in this graph, what we're seeing is the velocity curves for stars in many different galaxies. Looks like we have 4 different ones here. And notice that the vertical axis is the speed of the stars, and the distance from the center of the galaxy is on the horizontal axis. The expectation is that these curves should drop off pretty sharply because in most of the galaxies the stars seem to be concentrated towards the center. However, we actually find that the curves don't drop off, they stay relatively level, and so that is inferring that there's matter that we cannot see, and that's why we call it dark matter. So remember that when we're talking about an object that's orbiting a central object, that the speed with which it moves has something to do with the mass that it's orbiting. And so when we're measuring the period of the orbit and the average distance, we can actually calculate the mass of the object that we're orbiting, and that's with this expression right here. Remember, we don't actually have to do the calculations. We just want to sort of understand that there's a definite way for this calculation to be done. And from that, we can also we can look at rotation curves when we talk about the speed and the distance from the center. If we look at a rotation curve for the planets, we find that it drops off kind of nicely as we go away from the sun. And so the similar expectation is to happen for galaxies. And the reason that this drops off is that as you move out, you're still orbiting the central object is just the sun, and you're only it's only the gravity of the sun that's influencing these orbits. And so you're not encountering any more mass, and that's why it drops off. However, if we look at the Milky Way galaxy and look at the curve, it kind of stays flat, which is telling us that the mass is more spread out than in the solar system. It's not concentrated at the very center in a single star, of course, but even though it seems to indicate more mass than stars that we observe. So that is why we think that there's some sort of dark matter, because of the fact that the curve ends up getting pretty level. It indicates that there's more mass further away from the center, but it's not mass that we can see, it's not due to the stars that we can see, and that's where we get the name of the dark matter. You might remember looking at this when we talked about the Milky Way and the amount of material that we see within the orbit of the Sun, indicated by its orbital speed, is much larger than however many stars we know exist in here. So basically we think that within our galaxy there's a large halo of this dark matter. We can also get rotation curves for other spiral galaxies by looking at the Doppler shifts of their stars as they're coming towards us and away from us. And this allows us to then calculate their orbital velocities. And so you see that for all these spiral galaxies, they have a relatively flat rotation curves, which indicates that there is dark matter in these galaxies, because the curves do not drop off as you'd expect, because in spiral galaxies there is a concentration of stars towards the center. We can also get some information from elliptical galaxies by looking at the broadening of the spectral lines, and that gives us information about the speed of the stars. And we find that those galaxies also seem to have dark matter. And it doesn't just stop within galaxies, it also seems to exist between galaxies. For instance, there are clusters of galaxies that we see in space, and when we look at the motion of them relative to each other, it seems to indicate that there is dark matter between them, because they're moving, we find their motion to be faster than we would expect if we were just considering them to be under the influence of the visible stars that we can see. And so from this we sort of conclude that in these clusters, almost 85% of the material should be dark matter, with only 2% being the stars. Another interesting effect that sort of tells us that the mass is visible is what we call gravitational lensing, which is literally the bending of light as it goes through some area where there's a lot of gravitational effect. It actually distorts space, and so the light ends up coming to us. If this is the real galaxy, it actually ends up bending and following different paths depending on where it passes through. But when we view it, we don't know that that light has bent, so we actually see an image of the galaxy along this line and along this line and also along this line. Sort of the images that are caused by the distortion of the light is what we refer to by gravitational lensing, because that distortion of the light was caused by the gravitational effects. And so this is another thing that is sort of, it really implies a very strong gravitational effect, which would also then imply that there must be a lot of mass there. Turns out this seems to be dark mass. So all of these things are indicating that there's large amounts of dark matter everywhere. So does it really exist? Well, there's really two ways of looking at this. We could say yes, it does exist, and what we're observing are the effects of the gravitational attraction that the dark matter yields. Or we could say that there's something inherently wrong with our understanding of gravity, and that's why we're inferring this dark matter exists, but it really doesn't. So, you know, this is how we have to approach things in science. We have to be open to all the possibilities. Gravity has been so well tested. It's been hundreds of years, and we've never found anything to indicate that our theory of gravity is incorrect. So most astronomers believe that dark matter does truly exist. And we do find that a lot of things that we see in the universe are very difficult to explain unless we can explain it through the existence of dark matter. So how dark is dark matter? Well, it's certainly not as bright as a star. And so what is it made up of? There's sort of two basic schools of thought of what dark matter could be made of. It could be just ordinary matter that's made up of protons, neutrons, and electrons, but it's too dark to detect with current instruments, something that's not giving off enough light to be seen. Or it's thought that maybe it could be a certain type of particle that doesn't interact with matter very often, that is like a neutrino. And these are called weakly interacting massive particles, or WIMPs for short. Presently, astronomers believe that this is the best bet for an explanation of what dark matter really is. We believe in WIMPs because there's not enough ordinary matter to make up the dark matter that we seem to be inferring, and we think that maybe these WIMPs could be left over from the Big Bang. And models involving WIMPs help to explain how galaxy formation works. So the last thing that we want to look at is dark energy. And basically, it has to do with sort of what our universe is doing and what we project to happen in the future. So basically, we know right now that we see evidence that in our universe there's an expansion. And so the idea is what will happen in the future. And what will happen in the future depends on, what force will win out. Is gravity going to pull our universe back into itself? Will that attractive force result in slowing down of the expansion? Will it stop it? Will it start to collapse it? And so these are sort of the options of how our universe could end up. It could be true that our universe will expand to a point where then gravitation will take over and then start to collapse it. And maybe the universe just keeps going through a cycle like this. Or perhaps the expanding universe will reach a point where it sort of stops expanding and just sort of stays in a steady state. Or maybe it will just keep expanding at a constant rate. Or finally, what if it accelerates and starts expanding even faster? Essentially, what we're talking about in terms of these different categories is what will win the battle. Will gravity win the battle, or will the force that's causing the acceleration win the battle? The different future points that we looked at really are different relative strengths of these two opposing forces. And so the fate of the universe does depend on how much dark matter it is, because if there's a lot of dark matter, gravity will win out. If there's sort of a critical amount, then it'll sort of reach some steady state. And if there isn't enough dark matter, it'll just keep accelerating. We actually expect that, the amount of dark matter we have will keep it to be sort of a coasting universe. But if we really look at our data, it looks like the universe is actually accelerating. And so this is where the idea of dark energy comes from. The idea that there's some other energy that we're not familiar with that is actually winning out over gravity and causing the expansion to increase. And so that's sort of what the idea is of dark energy. There's not a lot of answers right now as to what it might be, but also in this slide, keep in mind that how old our universe might be will depend on what kind of future we have, because if we have an accelerating universe, it would have actually taken longer for it to get to its current point than if we had a coasting universe. And these are just things showing data from showing which kind of universe we think we have. And we see that it seems to sort of be aligning with the idea of an accelerating universe. And that's it for our class. I hope you had a good time and you learned a lot.